Hi everyone, my name is Amanda Ullman and I'm a PhD student here at UNC Chapel Hill. Today I'll be discussing a study that I performed with my advisor, Dr. Noah Kittner, on assessing the life cycle environmental impacts of liquid hydrogen production in La Guajira, Colombia. Colombia has a very diverse energy profile. Its northernmost department of La Guajira, which is circled in red here on the map, has the largest open-pit coal mine in South America. Interestingly, the country uses only a small portion of the coal it produces, and instead exports most of its coal to countries around the world. La Guajira also has incredibly plentiful wind resources, about 18 gigawatts of capacity. However, the department also has the highest poverty levels in the Caribbean region, and is home to large populations of indigenous and Afro-Colombian households. Given these energy resources and the economic vulnerability of its communities, developing new industries like hydrogen is of great interest to departments like La Guajira. Colombia has also stated goals of reducing its energy sector emissions by 35% by 2023, so understanding environmental impacts of any transition strategy is going to be critical for assessing local environmental justice implications and environmental implications in general. One strategy that Colombia plans to use to support its energy transition is hydrogen production, given hydrogen's ability to complement the intermittency of renewable energy resources and its use as a long-duration storage option and zero-emissions fuel. Hydrogen also has great potential to be produced from Colombia's coal and wind resources, which are also prime candidates for hydrogen production in Europe. This summer, Colombia launched its hydrogen roadmap, which noted the country's plans for producing 50 kilotons of hydrogen by 2030, particularly in La Guajira. Colombia also noted its goal to eventually export hydrogen to other countries, potentially to Europe, Asia, and North America, where there is growing demand for hydrogen. At this time, few studies have modeled the impacts of scaling up hydrogen production on greenhouse gas emissions, air pollution, and the environment. This study quantifies these impacts across the life cycle of hydrogen production to aid evaluation of whether Colombia's hydrogen plan can contribute to its carbon reduction targets and overall sustainability. A life cycle assessment provides a normalized and rigorous way to compare environmental impacts of upstream hydrogen production pathways. Hydrogen production sustainability is largely attributed to how hydrogen is produced. This study considers three types of hydrogen production pathways, which represent the three main classes of hydrogen. Gray hydrogen is produced using fossil fuels like natural gas or coal. Blue hydrogen is also produced from fossil fuels, but uses carbon capture and storage technologies to reduce its emissions. Green hydrogen is produced from zero-emissions electricity sources like wind and solar, using an electrolyzer to split water into pure oxygen and hydrogen. The intensity of environmental impacts resulting from hydrogen production will thus vary based on the mode of production used. This study considers two main hydrogen production processes, gasification and electrolysis. In the gasification process, coal is gasified in a gasification plant. Pure hydrogen is then separated out of the syngas produced by the gasification process using pressure swing adsorption. In the electrolysis process, electricity can come from the grid or from a dedicated power source to separate water into pure hydrogen and oxygen, as mentioned before. This study looks at 6 production scenarios: coal gasification with and without carbon capture and storage, electrolysis using electricity produced by a coal power plant, electrolysis using electricity produced by a local wind farm with electrolysis taking place on or off-site the wind farm, and finally electrolysis using electricity sourced from the country's national electricity grid. The functional unit of the study is 1 ton of liquid hydrogen. Each study is evaluated on the cradle-to-grave greenhouse gas emissions, air pollutant emissions, trace metal emissions, and water consumption based on the production of the functional unit. Here we can see the steps associated with the life cycle of each scenario. As we can see in scenario number 1 and number 2, the process is analyzed starting with the production of the coal in La Guajira's local coal mine, construction of the gasification plant, transportation of coal to the gasification plant, gasification of coal with and without carbon capture and storage, construction of the liquefaction plant, and finally, liquefaction of the hydrogen. The impacts for each step are calculated relative to those that would result from production of 1 metric ton of liquid hydrogen, which again is the unit of analysis for the study. Note the differences in the wind electrolysis scenarios shown on the slide, which vary based on the location of the electrolyzer and the liquefaction plant. In this study, we modeled 2 different ways to site the electrolyzer and liquefaction plant. In scenario number 1, the electrolyzer and liquefaction plant are sited next to a wind farm. A truck is then used to move the hydrogen to the port. The second scenario uses a transmission line to transmit the electricity produced by the wind farm to an electrolyzer and plant that are sited directly at the port itself. Using the EcoInvent database and power plant and grid characteristics specific to Colombia, we were able to assess the production of 3 different greenhouse gases, 5 air pollutants, 18 trace metals, and overall water consumption levels associated with each of our 6 scenarios. Our analysis found that the CO2 emissions associated with our coal electrolysis pathway were extremely intensive. This is represented here in the graph, with the x-axis representing the 6 scenarios and the y-axis showing the CO2 emission levels in tons, with emissions from each step of the scenario illustrated by a different color. The coal electrolysis scenario's emissions were a shocking 10 times that of the wind scenario. The step-by-step analysis also showed that most of the wind scenario emissions were resulting from the construction of the liquefaction plant, which is represented in gray. However, in the coal electrolysis scenario, most emissions were produced during electricity production, shown here in dark red. This led us to consider the effects of carbon capture and storage. We found that gasification without CCS has about 5 times the emissions of the wind scenarios, while adding in the CCS reduces that amount to just under 2 times that of wind. We can also see that siting the electrolyzer on or off-site makes virtually no difference for the carbon dioxide emissions. In our study, we also used Colombia's 50 kiloton hydrogen production goal to estimate annual impact levels. As was the case in the last chart, we used our x-axis to represent our 6 different scenarios, while the y-axis shows the impact category's respective annual emission or water consumption level. As we mentioned, Colombia has goals to reduce its energy sector emissions by 35% to maintain emissions levels at about 51 megatons of carbon dioxide equivalent emissions per year. We found that pursuit of the coal electrolysis scenario would add about 3.3 megatons of carbon dioxide equivalent emissions to its annual emissions total. This would require Colombia to reduce an extra 3.3 megatons from its energy sector emissions to successfully meet its reduction goals. By contrast, wind electrolysis would add just 0.3 megatons of CO2e emissions per year. We found a similar case with annual water consumption levels, shown in units of million cubic meters on the graph. We found that the coal electrolysis scenario consumes 64 times the water of the wind electrolysis scenario. The grid electrolysis scenario consumed 14 times that of wind. This is incredibly concerning given the challenges La Guajira has already faced with local drought. Our findings indicate that on an average dry year, the coal electrolysis scenario would consume almost 1/3 of the department's available water. In contrast, the wind electrolysis scenario would consume only 0.5% of the local water resources. Our findings also raise concerns over increased emissions of VOCs, NOx, lead, and mercury from hydrogen production from the coal-based scenarios. We found that the coal electrolysis scenario was associated with an increase of 34 kilotons of VOC emissions and 9.5 kilotons of NOx emissions, which raised concerns for photochemical smog formation in the region. Additionally, we found that the coal electrolysis scenario would emit over 1 ton of lead and about 110 kilograms of mercury. These emissions are important for considerations of community health, particularly given lead's association with brain damage and detrimental reproductive effects, and mercury's association with mental disorder and damage to nervous systems. Finally, our findings offer a nuanced understanding of the use of CCS technologies, which require greater coal input levels to produce the 1-ton liquid hydrogen output that gasification processes without CCS produce. Our findings indicate that these increases would result in VOC emissions that were 7 tons greater than those of the non-CCS gasification scenario, and lead emissions that were 50 kilograms greater than that of the non-CCS scenario. Taking a step back, these results provide us with an understanding of the environmental factors that Colombia might consider when developing its national hydrogen strategy. First, we can see that the electrolyzer siting decisions really have little impact on the indicators we analyzed here. However, local community perspectives, especially those of indigenous communities living on ancestral land, should be prioritized when considering infrastructure siting decisions. Policymakers should also consider manufacturing locations of equipment for hydrogen production infrastructure, like wind turbines and liquefaction plant parts, when analyzing localized impacts like air pollution and water consumption. For instance, should infrastructure be manufactured abroad, some of the impacts would then take place in other countries and could result in a lessened impact level on local communities. However, our analysis does find that much of the intensity of the impacts arises from the electricity generation processes that would take place in Colombia itself. Since climate change is expected to increase drought intensity in La Guajira, some scenarios could have the potential to exacerbate threats to communities' access to local water resources, which could affect community health and agricultural practices. While we found that technologies like CCS are effective in reducing carbon dioxide emissions from electricity generation, the technology resulted in greater emissions of other pollutants. Also, any infrastructural development associated with fossil fuels could have long-term implications for the country's fossil fuel dependence by contributing to carbon lock-in and increasing the likelihood of Colombia's consumption of fossil fuels for many years to come. Thank you for your time in viewing this presentation. If you have any questions or would like more information, please feel free to contact me, Amanda Ullman, by email at anu@unc.edu.